What if everything you know about physics is backwards? Picture a universe where time flows in reverse, where stars burn with antimatter instead of matter, and where the fundamental laws that govern reality are flipped like a reflection in a mirror. This isn't science fiction, it's a radical idea some scientists are seriously exploring: the anti-universe, a realm where every rule we take for granted is inverted, creating a cosmic paradox that challenges our deepest understanding of existence. Imagine standing at the edge of this mirror cosmos, watching as galaxies spin counterclockwise, as particles move backward through time, as gravity repels instead of attracts. It sounds impossible, yet the mathematics behind it might just hold up. Some theories suggest our universe could have a hidden twin, a shadowy counterpart born from the same explosive beginning but governed by opposite physics. This isn't just a thought experiment, it's a frontier of modern cosmology that could rewrite everything we thought we knew about the Big Bang, dark matter, and even the arrow of time itself. Why does this matter? Because the anti-universe isn't just a wild idea. It's a key that might unlock mysteries our current models can't explain. What if dark matter isn't some elusive substance but simply the gravitational echo of this mirrored reality? What if the universe's expansion isn't slowing down but being pulled by its own inverted twin? These questions aren't just mind-bending, they're gateways to a deeper truth about the fabric of reality. So let's dive into this astonishing concept, peeling back the layers of a theory that could turn physics upside down literally. By the end of this journey, you might never look at the cosmos the same way again. The idea of an anti-universe didn't just emerge from wild speculation. It has roots in one of the most fundamental symmetries in physics, CPT symmetry. This principle states that if you flip a particle's charge, mirror its position in space, and reverse the flow of time, the laws of physics should stay exactly the same. It's like holding up a cosmic mirror to reality and finding everything still makes perfect sense. But here's where things get mind-blowing. What if that mirror isn't just a mathematical trick? What if it's an actual alternate universe, born at the same moment as ours, but with every fundamental property flipped? That's the radical proposal put forward by physicists like Dr. Neil Turok. His work suggests that our universe might have a twin, a mirror image born from the same Big Bang, but governed by opposite rules. In this anti-universe, time would flow backward from our perspective. Particles would carry opposite charges, and even the structure of space itself could be inverted. It's as if the Big Bang wasn't just a single explosive beginning, but a cosmic collision between two realities, each pushing the other into existence. This theory doesn't just challenge our understanding of the universe, it rewrites the story of the Big Bang itself. Conventional cosmology paints the Big Bang as a singular, fiery origin point. But if Turok's idea holds, that moment wasn't an explosion at all. It could have been a symmetry-breaking event where one unified reality split into two mirrored halves. Instead of a chaotic beginning, the Big Bang might have been a perfectly balanced act of creation, with our universe and its twin emerging like reflections in a cosmic mirror. Why would physicists take such a bizarre idea seriously? Because the math works. CPT symmetry isn't just a quirky observation, it's deeply embedded in the equations of quantum mechanics. If the symmetry holds universally, then an anti-universe isn't just possible, it might even be necessary to keep the books balanced. Think of it like a cosmic ledger. For every particle in our universe, there could be an inverted counterpart in the mirror realm, ensuring the total energy of existence stays at zero. Turok's theory also offers surprising solutions to some of cosmology's biggest mysteries. Take dark matter, the invisible stuff that makes up most of the universe's mass. What if it's not some exotic particle, but simply the gravitational pull of the anti-universe bleeding into ours? Or consider the puzzling uniformity of the cosmos. the fact that distant regions of space look eerily similar despite never having been in contact. A mirrored twin could explain that too, acting as a hidden partner that shaped our universe from the very beginning. Of course, not everyone's convinced. Critics argue that an anti-universe might be mathematically elegant but impossible to test. How do you observe a realm where time runs backward and gravity pushes instead of pulls? But that's the beauty of theoretical physics. It pushes us to imagine the unimaginable, to question the very foundations of reality. Whether the anti-universe exists or not, the idea forces us to think bigger, to consider that our cosmos might be just one half of a grander, stranger whole. And if that's true, the answers to our biggest questions might be hiding in the mirror. To truly grasp the idea of an anti-universe, we need to understand CPT symmetry, the cosmic rulebook that might make such a mirror realm possible. At its core, this principle is built on three fundamental transformations: charge, parity, and time. Let's take them one by one. First, charge conjugation, or C-symmetry, flips a particle's electrical charge, turning an electron into a positron or a proton into an antiproton. It's like swapping every positive and negative sign in the universe's equations. Next comes parity, or P-symmetry, which mirrors spatial coordinates. Left becomes right, up becomes down, as if reality itself were reflected in a funhouse mirror. Finally, there's time reversal, T-symmetry, where the arrow of time flips direction, making cause and effect run backward like a rewinding film reel. Individually, these symmetries don't always hold. For example, certain weak nuclear force interactions violate parity. Nature seems to prefer left-handed particles in specific decays, which shocked physicists in the 1950s. Similarly, some quantum processes look different when time is reversed, breaking T-symmetry. But here's the astonishing part. When you combine all three, charge, parity, and time, physics insists the universe must remain unchanged. CPT symmetry is the ultimate cosmic balancing act, a rule so robust that no experiment has ever violated it. This isn't just abstract math. Visualize a particle like an electron, apply CPT, and you get a mirror image positron moving backward through time. Now scale that up. If the entire universe obeys CPT symmetry, then flipping all three properties at once should produce a valid alternate reality, one where antimatter stars shine, gravity repels, and time flows in reverse relative to ours. It's not science fiction, it's a direct consequence of the equations physicists use every day. The implications are staggering. If our universe has a CPT mirror twin, it could explain why the Big Bang left behind so little antimatter. In this picture, the antimatter didn't vanish, it simply became the building blocks of the anti-universe. The symmetry also hints at why our cosmos appears so finely tuned. Any asymmetry in our laws of physics might be perfectly counterbalanced by the flipped laws of its twin, like two sides of a scale keeping the multiverse in equilibrium. But how could we ever detect such a mirror realm? Since it's causally disconnected from us, time there runs backward from our perspective. Direct observation seems impossible. Yet some theorists propose subtle signatures. Gravitational waves from the early universe might carry imprints of this symmetry, or the mysterious uniformity of the cosmic microwave background could hide clues of a mirror image Big Bang. Even dark energy's acceleration might reflect a tug of war between our universe and its inverted counterpart. CPT symmetry isn't just a quirky footnote in physics textbooks. It's a lens that reshapes how we view reality's deepest layers, suggesting that every particle, every force, even time itself might have a hidden twin waiting to be discovered. Whether the anti-universe exists or not, the mere possibility forces us to confront a profound truth. The cosmos might be far stranger and far more symmetrical than we ever dreamed. If the Big Bang wasn't the beginning we've always imagined, but instead a mirror reflecting reality into two opposing halves, then the story of our universe takes on a breathtaking new shape. Picture this moment not as an explosion from nothingness, but as a symmetry-breaking event where one unified state fractured into twin realities, each expanding away from the other like ink blots in a cosmic Rorschach test. On one side, our familiar universe with its matter, forward-flowing time, and attractive gravity. On the other, its inverted twin, antimatter, reverse causality, and repulsive forces. This idea transforms the Big Bang from a singular origin into a collision of dimensions, a moment where physics itself bifurcated. Think of it like dropping a pebble into a perfectly still pond. The splash sends ripples outward in all directions, but what if the water's surface were just a boundary? Below it, an identical set of ripples might expand downward, mirroring the ones above. The Big Bang, in this view, becomes that initial splash, creating symmetrical waves of reality traveling in opposite directions through the fabric of existence. The elegance of this model lies in its ability to resolve long-standing cosmic puzzles. Take the mystery of antimatter's scarcity. In our universe, matter dominates, but according to fundamental physics, the Big Bang should have created equal amounts of matter and antimatter. So where did all the antimatter go? The mirror universe theory offers a stunning answer. It didn't disappear. Instead, it became the foundation of the anti-universe, a parallel realm where antimatter stars burn and particles with opposite charges dance to the tune of reversed physical laws. Even the accelerating expansion of our universe could find an explanation in this mirrored cosmology. If the anti-universe's gravity operates inversely, its repulsive force might be pulling on our cosmos from the other side of the Big Bang, acting as an unseen driver behind dark energy's mysterious push. This wouldn't just connect two universes, it would weave them into a single, interdependent system, where the behavior of one is forever tied to the other. Of course, such a radical reimagining of the Big Bang raises provocative questions. If time flows backward in the anti-universe, does that mean events there are unfolding in reverse order from our perspective? Would an observer in that realm perceive our universe as the inverted one? The answers might lie in the nature of causality itself. In this mirrored model, cause and effect could be relative, with each universe's past pointing toward the Big Bang like arrows aimed at the same center from opposite directions. The beauty of this theory isn't just in its explanatory power, it's in how it reframes our place in the cosmos. We might not be living in a lone universe with a definitive beginning and end, but rather one half of a grander duality, a reflection in an endless cosmic mirror. Whether this vision holds up to future tests or not, it reminds us that the universe's deepest truths often lie beyond the limits of our intuition, waiting in the shadows of symmetry to rewrite the stories we thought we knew. Antimatter isn't just the opposite of matter. It's the cornerstone of the anti-universe, a realm where everything we know is flipped on its head. In our universe, matter reigns supreme, from the stars above to the atoms in our bodies. But in its mirrored counterpart, antimatter takes center stage, weaving a cosmos where particles like positrons and antiprotons form the fabric of reality. The question isn't just why antimatter dominates there, it's why our universe ended up with so little of it in the first place. Consider what happens when matter and antimatter collide: annihilation. A single electron meeting its antiparticle, the positron, unleashes a burst of pure energy, erasing both from existence in a flash of gamma rays. If the Big Bang created equal amounts of matter and antimatter, as physics suggests, why didn't the universe annihilate itself instantly? The answer might lie in the anti-universe. While our cosmos emerged with a slight excess of matter, its twin could have tipped the scales in the opposite direction, collecting the leftover antimatter like cosmic crumbs from a shared table. This asymmetry is one of physics' greatest unsolved mysteries. Experiments show that particles and antiparticles don't always behave identically, a violation known as CP symmetry breaking. Tiny differences in their interactions during the universe's first moments might have allowed matter to dominate here while antimatter flourished elsewhere. Think of it like a coin toss at the birth of reality. Our universe landed on heads and the anti-universe landed on tails. But what if the anti-universe didn't just passively inherit antimatter? What if it actively shaped our own? Some theories suggest that the repulsive gravity of the mirror realm could have pushed matter away during the Big Bang, creating a cosmic divide that preserved both worlds. Alternatively, the anti-universe's backward arrow of time might mean that what we perceive as annihilation events here are actually creation events there, like watching a film in reverse, where explosions reassemble into pristine structures. The implications are staggering. If the anti-universe is brimming with antimatter, it could explain why our searches for antimatter galaxies have come up empty. They're not missing, they're simply hiding in the mirror. Even dark matter's elusive nature might be tied to this imbalance, with the gravitational whispers of antimatter stars tugging at our universe from beyond the veil. So did the anti-universe win the antimatter battle? Maybe it's not about winning or losing, but balance. Like two sides of a Mobius strip, our realities could be fundamentally linked, each completing the other in a grand cosmic symmetry. The universe we see might just be one half of a far larger, far stranger whole where every particle here has its counterpart there, and every law of physics finds its opposite. The search for answers isn't just about understanding antimatter, it's about uncovering the hidden mirror that could redefine existence itself. In the anti-universe, time doesn't just tick backward, it unfolds in a way that would make our heads spin. Here, entropy, the measure of disorder we watch steadily increase in our world, actually decreases with every passing moment. Picture a shattered vase reassembling itself on its own, or smoke curling back into a cigarette instead of dissipating. These aren't just quirks, they're the inevitable results of a cosmos where the arrow of time points in the opposite direction. Now, imagine beings living in this inverted reality. For them, the future isn't uncertain, it's as fixed as our past. They might remember events that haven't happened yet from our perspective, while their past feels hazy, like a dream slipping away. Think of it like watching a movie in reverse. To us, it's unnatural, but to them, it's the only way existence makes sense. Their lives would unfold in what we'd call reverse order, aging backward with deaths preceding births and cause and effect flipped on their heads. A cup wouldn't fall and break, it would leap from the floor into their hands perfectly whole. This bizarre flow of time isn't just a parlor trick, it's woven into the fabric of their physics. In our universe, entropy drives time's arrow, pushing systems toward chaos. But in the anti-universe, the second law of thermodynamics works in reverse, guiding everything toward order. A melted ice cube would refreeze spontaneously, and scattered particles would arrange themselves into intricate patterns without external influence. To an observer from our world, it would look like miracles happening everywhere, but to them, it's just the mundane march of time. The real mind bender, both perspectives could be equally valid. Just as a train moving past you might appear to be in motion while someone on board feels stationary, time's direction might be relative to which universe you call home. An anti-being might argue that our time is backward, watching in bafflement as we age toward decay rather than rejuvenation. This duality forces us to confront a profound question. Is time's flow an absolute truth or just a matter of cosmic perspective? Even more intriguing are the implications for consciousness. If beings in the anti-universe experience time in reverse, does that mean their thoughts unfold from conclusion to premise? Would a conversation with them sound like listening to a recording played backward, or would their brains process information in a way we can't even fathom? Some theorists suggest that consciousness itself might be a product of entropy's direction, meaning their minds could operate in a fundamentally alien way, turning our assumptions about free will and memory inside out. This isn't just philosophical musing. If the anti-universe exists, its reversed time could leave subtle fingerprints on the fabric of reality. Quantum entanglement, for instance, might behave differently near the boundary between universes, offering a potential window into this mirrored realm. Or gravitational waves from the early cosmos could carry echoes of a time when both universes were intertwined, a faint whisper of the moment physics split in two. The deeper we dig, the clearer it becomes. Time's arrow might not be universal. It could be a local quirk, a habit of our particular slice of existence. The anti-universe challenges us to rethink not just the nature of time, but the very meaning of before and after, suggesting that what we call the past and future might just be two sides of the same cosmic coin. Dark energy's mysterious push on our universe might hold the key to uncovering its mirrored twin. For decades, scientists have grappled with why the cosmos isn't just expanding, it's accelerating, as if some invisible force is stretching space itself apart. But what if that force isn't coming from within our universe at all? Imagine the anti-universe acting like a cosmic anchor, its gravitational pull operating in reverse. While our universe expands, its twin could be contracting, creating a tension that manifests as the very dark energy we measure. Think of it like a cosmic seesaw. On one side, our universe flies outward, galaxies rushing away from each other. On the other, the anti-universe collapses inward, its time-reversed physics pulling matter together instead of apart. The balance between these opposing motions could explain why dark energy's effects seem so finely tuned, not as some arbitrary constant, but as a natural consequence of symmetry between two intertwined realities. This wouldn't just solve the mystery of dark energy, it would weave it into the fabric of a grander cosmic dance. The math behind this idea is startlingly elegant. General relativity describes gravity as the curvature of space-time, but it doesn't dictate which way that curvature should bend. In the anti-universe, gravity could behave like a repulsive force, warping space-time in the opposite direction. As our universe stretches, its twin's inverted gravity might exert a kind of negative pressure, creating the illusion of dark energy's push from within our own cosmos. It's like feeling the wind on your face while standing still. What seems like a force acting on you might actually be the motion of everything else around you. There's even observational support for this link. The cosmic microwave background, the afterglow of the Big Bang, shows puzzling large-scale patterns that standard cosmology struggles to explain. Some physicists argue these anomalies could be signatures of an anti-universe's gravitational influence, imprinted on our reality during that primordial symmetry-breaking moment. The universe's expansion rate, too, might carry hints of this mirroring. If dark energy's strength isn't constant but subtly changing over time, it could reflect the shifting balance between our expanding realm and its contracting counterpart. Critics raise valid objections, of course. If the anti-universe is causally disconnected from ours, how could its contraction affect us? The answer might lie in quantum entanglement, a phenomenon where particles remain mysteriously linked across vast distances. On a cosmic scale, entanglement could tether our universe to its twin through the Big Bang itself, allowing their fates to remain intertwined even as they drift apart. Alternatively, the boundary between the two realms might not be as absolute as it seems, with gravitational waves or other quantum effects bridging the divide. Whether this explanation holds up or not, the sheer possibility reshapes how we view dark energy. No longer just a placeholder for our ignorance, it becomes a potential window into a mirrored reality, a clue that our universe is part of something far larger and stranger. The acceleration we measure might not be an endpoint, but a cosmic echo, a ripple in the fabric of existence reminding us that the story of the cosmos is still being written in two directions at once. Black holes have long been the universe's ultimate enigmas, cosmic traps where gravity becomes so strong, not even light can escape. But what if these monstrous voids aren't just dead ends? What if they're bridges to the anti-universe, funneling matter and energy into a realm where physics runs in reverse? The idea isn't as far-fetched as it sounds. Einstein's equations actually hinted at this possibility nearly a century ago with the concept of Einstein-Rosen bridges, more popularly known as wormholes. These hypothetical tunnels through spacetime could, in theory, connect black holes in our universe to their opposite counterparts, white holes in the entire universe. White holes are the yin to black holes' yang. While black holes suck everything in, white holes would spew matter and energy outward like a cosmic fountain that nothing can enter. If a black hole in our universe linked to a white hole in the entire universe, it would create a two-way street between realities, a place where the inward crush of a singularity here becomes an explosive burst there. Picture a river flowing over a waterfall only to emerge from a geyser in another world. The mathematics even allows for it. Einstein's general relativity doesn't care which direction time flows, meaning a black hole's event horizon in our universe could seamlessly become a white hole's eruption point in its mirrored twin. Hawking radiation adds another layer of intrigue. Black holes aren't entirely black, they slowly leak energy due to quantum effects near their edges, fading away over eons. But if a black hole connects to an anti-universe white hole, that radiation might not be random noise, it could carry encoded information about the mirror realm. Imagine decoding the Hawking glow and finding subtle patterns that reveal the structure of antimatter galaxies or the inverted laws of physics on the other side. It's like intercepting a message in a bottle washed ashore, only to realize it was tossed into the ocean from a parallel world. The implications are staggering. If black holes are portals, they might not destroy information but transfer it, resolving the infamous information paradox that puzzled even Stephen Hawking. Every particle swallowed by a black hole in our universe could re-emerge in the anti-universe, preserving the total balance of reality. This would mean the cosmos has a built-in recycling system where nothing is ever truly lost, just transformed and transported across the mirror divide. Even the fate of civilizations could hinge on this connection. A species teetering on the edge of a supermassive black hole might not face annihilation but transmutation, their very essence rewritten into the fabric of an opposite reality. Of course, the challenges are immense. Wormholes, if they exist, are likely unstable, snapping shut faster than anything can traverse them. The extreme conditions near a black hole's core would shred any matter into unrecognizable forms. And detecting a white hole's output in the anti-universe is, for now, beyond our reach, like trying to hear a whisper from the other side of a soundproof wall. Yet the mere possibility reshapes how we view these cosmic beasts. They might not be the end of the road, but crossroads, points where universes touch, and the impossible becomes just another thread in the tapestry of existence. Whether they're true bridges or mere mathematical curiosities, black holes as portals remind us that the universe's deepest secrets often lurk where our intuition fails. Neutrinos are the universe's ultimate ghost particles, so elusive they can pass through light years of lead without a single interaction. But what if their strangeness isn't just a quirk of quantum mechanics? What if these shadowy particles are actually messengers from the anti-universe, slipping through cracks in reality to bring us whispers of a mirrored cosmos? Unlike any other known particle, neutrinos seem to flirt with the boundaries of physics, behaving in ways that make scientists wonder if they're governed by rules we haven't yet discovered, or rules from a reality where everything is inverted. Take the Anita experiment, a high-altitude balloon floating over Antarctica. Its mission was simple: detect high-energy neutrinos from space. But in 2016 and 2018, Anita spotted something impossible: neutrinos not coming down from the cosmos but up from the Earth itself. These particles appeared to be traveling backward through the planet as if it were transparent, defying all expectations. One explanation: these weren't ordinary neutrinos. They could have been particles from the anti-universe where time flows in reverse. To them, Earth's matter might be intangible, allowing them to pass through unimpeded while our detectors catch fleeting glimpses of their passage. The math behind this is tantalizing. Neutrinos already break one of physics' most cherished symmetries, parity. They spin in only one direction, like cosmic tops that refuse to wobble the other way. If the anti-universe exists, its neutrinos might spin the opposite way, effectively carrying a hidden signature of their mirrored origin. When these particles occasionally cross into our realm, they'd appear to move backward through time from our perspective, like a video played in reverse. This wouldn't just solve the Antimatter mystery, it could rewrite our understanding of how particles interact across dimensional boundaries. Even more intriguing is the role neutrinos played in the early universe. Moments after the Big Bang, neutrinos outnumbered all other particles combined. If some of them were actually visitors from the anti-universe, they could have subtly shaped the cosmos we see today. The slight matter-antimatter imbalance that allowed our universe to exist, that might have been nudged into place by neutrino interactions, we're only beginning to comprehend. It's as if these particles were cosmic diplomats, negotiating the terms of reality between two opposing realms. Of course, not every physicist is ready to embrace this radical idea. Skeptics argue that the Antimatter anomalies could stem from mundane sources, instrument glitches, unknown astrophysical phenomena, or even exotic types of dark matter. But the possibility remains. Neutrinos might be the only particles nimble enough to dance between universes, carrying secrets in their spin and speed that could reveal the true nature of existence. If we learn to read their signals, we might finally find the footprints of a world where physics runs in reverse, a hidden twin to our own, waiting just beyond the edge of perception. Quantum entanglement might not just be strange, it could be the invisible thread stitching our universe to its mirrored twin. Imagine two particles born together, forever linked no matter how far apart they drift. Change one and the other instantly responds, as if space and time between them don't exist. Einstein called this spooky action at a distance, but what if the spookiness runs deeper? What if these particles aren't just communicating across our universe, they're whispering to their counterparts in the anti-universe? Take Schrödinger's infamous cat, trapped in a box where it's both alive and dead until someone looks. Now picture this, the cat isn't just in two states here, it's alive in our universe and dead in the anti-universe simultaneously. The moment you open the box and collapse the possibility into one outcome, its mirrored twin does the opposite. It's as if reality itself is playing a cosmic game of seesaw, with every decision here tipping the scales there. This isn't just a thought experiment, it's a radical reimagining of entanglement where particles aren't bound by distance but by dimensions. The math behind this is eerily beautiful. In quantum mechanics, entangled particles share a single quantum state described by a wave function that spans both. If the anti-universe exists, that wave function could stretch across the mirror divide, with each particle's fate tied to its inverted twin. Measure an electron's spin as up here, and its counterpart in the anti-universe would instantly snap to down, not because of faster-than-light signals, but because they were never truly separate to begin with. It's like two sides of the same coin, flipped into opposing realities. This idea could explain some of quantum theory's biggest headaches. Why does observation force particles to choose a state? Maybe the act of measuring here forces a corresponding collapse there, balancing the cosmic books, even the uncertainty principle, the rule that we can't know a particle's position and momentum simultaneously, might reflect a deeper symmetry. The more precisely we pin down a particle's location in our universe, the more its anti-universe twin's momentum becomes definite, as if reality compensates across the mirror. But how could we ever test such a wild idea? Surprisingly, there might already be clues. Quantum experiments have shown entangled particles behaving in ways that defy classical physics, as if influenced by forces outside our universe. Some theorists suggest that anomalies in these experiments, tiny deviations from expected results, could be fingerprints of the anti-universe's presence. It's like hearing an echo in a silent room and realizing there's a hidden chamber behind the wall. The implications are staggering. If entanglement bridges universes, then every quantum decision here ripples into a mirrored reality. Stars exploding, civilizations rising, even your morning coffee cooling, all could have inverted counterparts unfolding in reverse on the other side. This isn't just physics, it's philosophy. It asks whether our choices are truly ours or part of a vast, symmetrical dance where every action has an equal and opposite reaction somewhere else. Whether this holds up or not, the idea pushes us to rethink the very fabric of existence. The universe might not be a solitary stage, but one half of an entangled whole, where particles dance in perfect sync with their mirror images, and reality is far richer and far stranger than we ever dreamed. In the anti-universe, gravity doesn't pull, it pushes. Picture standing on a planet where the ground repels you, where the act of falling means being hurled into the sky. This isn't just a tweak to Newton's laws, it's a complete inversion of how forces shape reality. While our cosmos is held together by gravity's relentless tug, binding galaxies and bending light, the mirror realm operates on cosmic repulsion. Stars don't form from collapsing gas clouds, but from matter being pushed together by an outward force, like marbles repelled into a fragile cluster, black holes. They'd function in reverse too. Instead of trapping light, they'd emit it violently, becoming radiant beacons in a sky where darkness is the exception. Light itself behaves unnervingly in this mirrored realm. Here, photons have positive wavelengths, cresting like ocean waves moving forward. There, light could carry negative wavelengths, with peaks and troughs inverted like a sound wave played backward. Imagine looking at an anti-universe star. Instead of emitting light, it might absorb it, appearing as a dark void surrounded by glowing halos where photons are sucked in. The night sky wouldn't be dotted with points of light, but with patches of shadow, as if the cosmos were a photographic negative of our own. Even rainbows would defy intuition, colors reversed with violet at the bottom and red at the top, like a spectrum flipped through a looking glass. Nuclear forces, the glue of atoms, turn disruptive in this inverted world. Protons and neutrons repel rather than attract, making atomic nuclei impossible under normal conditions. Matter wouldn't coalesce into familiar elements but fragment into chaotic plasma, held together only by the anti-universe's reversed electromagnetism. Chemical reactions would unfold backward, with compounds breaking down into simpler forms instead of forming bonds. Water might unboil itself, ice could crystallize spontaneously from vapor, and flames would draw heat from their surroundings like inverse fires. Yet the most startling consequence is how these inverted laws reshape celestial mechanics. Our planets orbit stars because gravity pulls them inward, but in the anti-universe, orbits would require a delicate balance between repulsive gravity and other forces. A planet could orbit by being constantly pushed away at just the right angle, tracing spirals instead of ellipses. Galaxies wouldn't spin, they'd unravel, their stars flung outward as if caught in a cosmic explosion frozen in time. Even the vacuum of space would behave differently. Quantum fluctuations might push particles apart instead of allowing temporary pops of existence, turning empty space into an active, rippling frontier. These aren't arbitrary twists, they're mathematically consistent transformations of known physics. Every law we take for granted has a mirror image counterpart, a shadow version that's equally valid under CPT symmetry. The anti-universe isn't breaking the rules, it's following a different set written in reverse. And if we ever found a way to peer into this realm, the view wouldn't just be unfamiliar, it would challenge our very definition of what's possible. If intelligent life exists in the anti-universe, their experience of reality would be as alien to us as time itself flowing backward. Imagine a civilization where technology doesn't advance toward complexity, but regresses toward simplicity, where inventions are not built but uninvented, where progress means dismantling rather than creating. Their history books would chronicle the careful deconstruction of machines into raw materials, the gradual abandonment of cities as populations shrink backward toward nomadic tribes, and the eventual return to primal harmony with nature. To them, our relentless innovation might look like chaos, a feverish march toward entropy. Communication between our worlds would be a paradox wrapped in a riddle. If their now is our distant future and their past is our tomorrow, any message we send would arrive in their timeline before we even conceived it. Picture an anti-universe scientist receiving our radio signals not as a first contact, but as an echo of a long-forgotten event, like hearing a thunderclap before seeing the lightning. Their attempts to reply might reach us eons before they sent them, tangled in a causal loop where effect precedes cause. Perception itself would be inverted. Where we see the universe expanding, they might witness it contracting, hurtling toward a singularity they remember as their Big Bang. Our night sky, filled with the faint glow of distant stars, might appear to them as a darkness punctuated by mysterious voids, regions where light hasn't yet begun to be absorbed by their anti-stars. Even their art and storytelling would reflect this reversal. Narratives starting with endings, symphonies resolving into silence, paintings fading into blank canvases. Could they even comprehend us as real? To an anti-universe observer, our actions might seem predetermined, our lives unfolding like a film played in reverse. Free will, for them, could be the illusion, a haunting sense that every choice we make was destined by their future. Their philosophers might argue that we are ghosts of a world that, from their perspective, is collapsing into order rather than evolving. Yet the most tantalizing question isn't just how they'd perceive us, but whether we're already entangled in ways neither civilization fully grasps. Quantum links between particles might stretch across the mirror divide, meaning their scientists' experiments could subtly influence ours and vice versa. A breakthrough in our universe could ripple backward into theirs as an inexplicable anomaly, a glitch in their equations hinting at a deeper connection. The chilling beauty of this idea lies in its symmetry. If both civilizations exist, neither is the correct version of reality. Just two halves of a cosmic dance, forever stepping in opposite directions, each convinced their arrow of time points the right way. Whether we could ever meet or even recognize each other as alive remains one of the universe's greatest unanswerable riddles, but the possibility alone stretches the imagination, revealing how narrow our view of existence might truly be. In the anti-universe, heat doesn't dissipate, it coalesces. Picture a frying pan left on a stove, glowing red with warmth. In our world, an ice cube dropped onto that pan would melt instantly, its orderly crystalline structure succumbing to chaos as molecules scatter into vapor. But in the mirror cosmos, the opposite unfolds. Wisps of steam rising from the pan's surface would suddenly snap together, locking into a perfect geometric lattice as an ice cube materializes from the chaos. This isn't magic, it's the inevitable consequence of a reality where the second law of thermodynamics runs in reverse. Entropy doesn't increase here, it decreases, turning randomness into regimented patterns with the same inevitability that drives our universe toward disorder. The implications are staggering. Where we see shattered glass that never reassembles, they'd witness fragments leaping back into whole panes, a drop of ink dispersing in water. To them, it's a swirling dance of particles that suddenly align into a single, ink-eyed droplet. Even the lifespan of stars would flip instead of burning out. Anti-stars might draw scattered energy from the void, growing hotter and more organized over time. This reversed arrow of entropy doesn't just tweak physics, it rewrites the narrative of existence itself. Consider what this means for complexity. In our universe, life fights against entropy, building temporary islands of order in a sea of chaos. But in the anti-universe, complexity might be the default state. Structures we consider miraculous, like DNA's double helix or the neural networks of a brain, could arise spontaneously, as fundamental to their cosmos as hydrogen atoms are to ours. A forest fire there wouldn't reduce trees to ash. It'd weave charcoal and smoke back into towering trunks and emerald leaves. The very concept of decay is alien in a realm where time's flow scrubs away disorder like an eraser on a chalkboard. Yet this cosmic mirror isn't perfect. The anti-universe's relentless march toward order creates its own paradoxes. Without the dissipative tug of entropy, energy couldn't spread evenly, leading to pockets of extreme cold where heat concentrates elsewhere. Their version of a black hole might not be a gravitational pit but a radiant vortex, drawing in chaos and spewing out perfect crystalline structures. Even their version of time travel would look bizarre. Reversing events wouldn't require bending physics, but simply waiting as the universe inevitably reconstructs the past from the scattered fragments of the future. Watching an anti-ice cube form teaches us more than just inverted physics. It reveals how deeply our intuition is tied to entropy's one-way street. Their reality isn't just backward. It's a testament to how fragile our assumptions are, how easily the cosmos could have chosen a different set of rules. And if that's true, the next great leap in understanding might not come from looking deeper into our universe, but from daring to peer into the mirror. Searching for proof of the anti-universe isn't like hunting for dark matter or distant galaxies. It's more like chasing a reflection in a foggy mirror. Scientists have devised ingenious ways to test whether our cosmos has a hidden twin, but every experiment runs headfirst into the same cosmic roadblock, the Big Bang's impenetrable veil. One approach involves scouring the universe for primordial antimatter, leftovers from the birth of reality that might have survived annihilation. If the anti-universe exists, pockets of ancient antimatter could linger at the edges of our cosmos, like echoes of a mirror that hasn't fully shattered. Balloon-borne detectors like the alpha magnetic spectrometer have spent years combing through cosmic rays, hoping to spot antihelium nuclei, a telltale sign that antimatter stars once burned in our own backyard. So far, they've found nothing, but the search isn't over. Every null result tightens the constraints on where or when the anti-universe might be hiding. Another strategy targets time-reversed particles, like those baffling Anita neutrinos that seem to emerge from Earth's core. If these aren't flukes but genuine messengers from the mirror realm, they'd carry a distinct signature, energies and trajectories that defy conventional physics. New experiments like the proposed Grand Observatory aim to catch more of these backward-moving particles, scanning the skies for cosmic rays that behave as if they're running the film of reality in reverse. The challenge, distinguishing between ordinary particle oddities and true fingerprints of the anti-universe, requires precision so fine it borders on philosophy. But the biggest hurdle isn't just technical, it's conceptual. If the anti-universe is behind the Big Bang, separated from us by that fiery Genesis moment, then no signal from there can ever reach us directly. It's like trying to hear someone on the far side of a waterfall. The roar of creation drowns out any whisper from beyond. This doesn't mean the idea is untestable, though. Cosmologists look for secondary clues, like subtle imbalances in the cosmic microwave background or anomalies in large-scale galaxy distribution. These could be shadows cast by the anti-universe's gravity, warping our cosmos from the other side of time. Even gravity waves might hold secrets. If the Big Bang sent ripples through space-time that still resonate today, their patterns could reveal whether the universe was born alone or with a twin. Future observatories like the Laser Interferometer Space Antenna could detect these primordial tremors, offering a glimpse past the Bang's blinding curtain. Until then, the anti-universe remains a tantalizing ghost, a theory so elegant it hurts to doubt it, yet so elusive it defies proof. Whether it's real or not, the hunt itself is reshaping how we see the cosmos, reminding us that some truths might not lie ahead in space but backward in time. The cosmic microwave background is more than just the afterglow of the Big Bang. It's a fossilized snapshot of the universe's infancy, imprinted with secrets we're still deciphering. Among its faint swirls and temperature variations, one anomaly stands out: a mysterious cold spot, a patch of sky where the CMB's glow dips unexpectedly. To most, it's just a statistical oddity, but to physicists probing the anti-universe, it could be the shadow of a mirror cosmos brushing against our own, like a hand pressing against the other side of a curtain. Think of the CMB as the cave wall in Plato's famous allegory. The shadows dancing across its surface, those tiny fluctuations in temperature aren't just random noise. They're projections of deeper structures, echoes of forces that shaped the universe moments after its birth. The cold spot, spanning nearly 1 billion light-years, defies easy explanation. Some argue it's a cosmic void, a barren stretch of space where matter is unusually sparse. But voids that large are statistically unlikely in our standard models. What if, instead, it's a gravitational imprint from the anti-universe, a region where its repulsive gravity subtly tugged on ours during the Big Bang, leaving a faint depression in the CMB's thermal tapestry? The math behind this is tantalizing. If the anti-universe exists, its inverted physics would have warped space-time differently in those early moments. While our universe's matter clumped under gravity's pull, its twin's repulsive force might have carved out a corresponding underdensity in our cosmos, like a sculptor pressing two lumps of clay together and leaving one side indented. The cold spot could be that indent, a cosmic bruise from a collision we can't directly see. Critics counter that such anomalies might just be flukes, cosmic lottery wins in a vast and varied universe. After all, if you roll the dice enough times, you'll eventually land a statistically improbable result. But here's where the plot thickens: the cold spot isn't alone. Other CMB anomalies, like oddly aligned temperature patterns dubbed the axis of evil, also resist conventional explanations. Together, they form a constellation of peculiarities that, while not definitive proof, align suspiciously well with predictions from mirror universe theories. It's as if the universe left breadcrumbs, subtle, ambiguous, but hauntingly consistent. The hunt for answers continues. Next-generation telescopes, like the Simons Observatory and CMB-S4, will map the CMB with unprecedented precision, searching for patterns that might betray the anti-universe's presence. If they find evidence of gravitational waves from the Big Bang twisted in unexpected ways, or temperature fluctuations that defy known physics, the cold spot could transform from a curiosity into a Rosetta Stone, a cipher decoding the existence of a reality beyond our own. Until then, it remains one of cosmology's most tantalizing maybes, a shadow on the cave wall pointing to something far stranger lurking just out of sight. If the anti-universe exists as our cosmic mirror, balancing every particle and force with its opposite counterpart, does that finally solve one of physics' greatest mysteries, the fine-tuning problem? Our universe seems impossibly precise. Tweak gravity by a fraction, alter the strength of the nuclear forces just slightly, and stars wouldn't shine, atoms wouldn't form, and life as we know it couldn't exist. Scientists have wrestled with this perfection for decades, calling it everything from luck to evidence of a multiverse. But the anti-universe offers a radical alternative. What if the universe isn't finely tuned at all? What if its apparent perfection is just half of a grander equation, with the mirror realm cancelling out every delicate balance we observe? This idea turns fine-tuning on its head. Instead of our universe being improbably perfect, it would be necessarily average, one half of a symmetrical whole where every extreme is mitigated by its opposite. The gravitational constant isn't arbitrarily precise. It's simply counterbalanced by the anti-universe's repulsive gravity. The scarcity of antimatter here isn't a puzzle. It's the natural result of antimatter dominating there. Even the vacuum energy driving cosmic acceleration might be neutralized by its twin's inverted expansion, like two tug-of-war teams pulling with equal force. Suddenly, the numbers that seemed suspiciously perfect become inevitable, the default outcome of a self-correcting cosmic duality. Yet this elegant solution raises its own philosophical questions. Does postulating an anti-universe genuinely explain fine-tuning, or does it merely relocate the mystery? After all, we'd still need to ask why the laws of physics allow for such symmetry in the first place. Why should CPT symmetry hold so perfectly that it births two mutually balancing realities? Critics argue this doesn't eliminate fine-tuning. It just shifts the improbability to a deeper level, demanding an even more fundamental reason for the symmetry's existence. It's like explaining a locked door by saying there's an identical key on the other side. You've doubled the puzzle rather than solving it. The debate touches on something profound, whether the universe's order requires an explanation at all. Some physicists, like Lee Smolin, argue that fine-tuning might be an illusion, a selection bias where we only notice the laws that permit our existence. Others, like Roger Penrose, see it as evidence of deeper layers to reality, perhaps even cyclical universes with evolving constants. The anti-universe theory stakes a bold middle ground, suggesting that what we call fine-tuning is really the shadow of a vaster, self-regulating system. This duality also hints at a deeper cosmic symmetry, one that transcends mere physics. If our universe and its mirror twin are two sides of the same coin, then existence itself might be fundamentally balanced not just in matter and antimatter, but in chaos and order, creation and destruction. Eastern philosophies have long embraced this idea, from the yin-yang of Taoism to the dualistic cosmos of Zoroastrianism. Even in modern science, the holographic principle suggests that our three-dimensional reality could be a projection of information encoded on a two-dimensional surface. The anti-universe might be the ultimate expression of this balance, a physical manifestation of the universe's need to reconcile opposites. But balance isn't the same as understanding. If the anti-universe exists, it doesn't just answer questions, it redefines them. Instead of asking why our universe is the way it is, we'd need to ask why duality is the default. Is symmetry itself a law deeper than gravity or quantum mechanics? Could there be a meta-principle governing all realities, ensuring that every universe comes paired with its inverse? These aren't just scientific questions, they're metaphysical ones, blurring the line between physics and philosophy. The anti-universe, then, isn't just a theoretical escape hatch from fine-tuning. It's a lens that refracts our deepest inquiries about existence, turning every why into a why not. Whether it's the ultimate answer or another layer of the puzzle, one thing is clear. The universe's secrets might not lie in looking deeper, but in learning to see sideways into the mirror. Long before physicists dared to propose an anti-universe, storytellers were already playing with the idea of mirrored realities. Take Christopher Nolan's mind-bending film Tenet, where characters manipulate inverted entropy, watching bullets fly back into guns and explosions reassemble shattered buildings. While Hollywood took creative liberties, the core concept, time running backward with its own set of physical rules, eerily parallels the anti-universe hypothesis. Nolan consulted physicists to ground the film's science, proving how art often dances on the edge of discovery, anticipating ideas that later emerge in equations. Comics have flirted with these concepts for decades. Marvel's Negative Zone, introduced in Fantastic Four in the 1960s, is a hauntingly prescient vision, an antimatter realm where laws of physics are flipped, accessible only through unstable portals. Sound familiar? It's almost as if Stan Lee and Jack Kirby tapped into a cosmic intuition, imagining a universe where heroes battle entropy itself. DC's Antimatter universe, home to the villainous Anti-Monitor, takes it further, painting a dystopian reflection of existence where destruction breeds order. These stories weren't just entertainment, they were cultural test runs for theories too radical for academia at the time. Mythology, too, has whispered of dual realities for millennia. The Taoist yin-yang symbolizes balance through opposition. Light cannot exist without dark, creation without destruction. Hindu cosmology describes the universe breathing in and out, expanding and contracting in cycles, while Norse myths speak of mirrored realms like Niflheim and Muspelheim, icy chaos meeting fiery order. These ancient narratives didn't have quantum field theory, but they grasped a profound truth that reality might require an equal and opposite counterpart to hold itself together. What's fascinating isn't just that pop culture predicted the entire universe, but how it did. Scientists often dismiss artistic interpretations as fantasy, yet history shows that imagination routinely paves the way for breakthroughs. Einstein visualized riding a light beam before relativity clicked into place. Kip Thorne brainstormed wormholes for Interstellar and ended up publishing peer-reviewed papers. The entire universe might follow the same path, from dismissed speculation to testable theory, with art as its accidental prophet. This back and forth between creativity and science reveals something deeper: humanity's instinct that reality is stranger than it seems. Whether through blockbuster films, comic book sagas, or millennia-old symbols, we've always sensed that the cosmos doesn't play by a single set of rules. The entire universe, once confined to the fringe of theoretical physics, now feels inevitable, not just because the math suggests it, but because our stories have been preparing us for it all along. The entire universe isn't without its skeptics, and their criticisms cut deep. One of the loudest objections: the idea might be mathematically elegant, but if it's impossible to test, is it really science or just sophisticated metaphysics? Even some respected physicists dismiss the concept as untestable speculation, no more grounded in reality than a thought experiment. After all, if the mirror universe exists before the Big Bang or beyond our causal horizon, how could we ever gather evidence to confirm it? This isn't just nitpicking, it strikes at the heart of what makes an idea scientifically valid. Without falsifiability, the ability to prove something wrong, theories risk drifting into philosophy. This criticism echoes debates around string theory's multiverse. Both ideas are breathtaking in scope, offering elegant solutions to cosmic puzzles, yet both struggle with the same hurdle: empirical proof. String theory posits countless unseen universes with different physical constants, while the entire universe suggests a single mirrored twin. The difference: string theory's extra dimensions and vibrating strings, for all their complexity, at least attempt to make predictions about particle physics we might one day observe. The entire universe, by contrast, seems locked behind the impenetrable wall of the Big Bang. Critics argue that makes it closer to metaphysics than physics, a beautiful idea with no clear path to verification. But defenders counter that absence of evidence isn't evidence of absence. They point to historical precedents where science leaped ahead of observation. Black holes were once deemed purely theoretical, their existence debated until technology caught up. The Higgs boson took half a century to detect. Even dark matter remains unseen, yet its gravitational fingerprints are undeniable. The entire universe might simply require a similar patience and ingenuity to uncover. Others argue the criticism misses the point. Science isn't just about what we can observe today, but about pushing the boundaries of understanding. The entire universe isn't just a wild guess. It's a natural extension of CPT symmetry, one of physics' most robust principles. If the math insists a mirror realm should exist, dismissing it because it's hard to test risks closing doors to potential breakthroughs. After all, quantum mechanics once seemed just as counterintuitive, yet now underpins everything from smartphones to MRI machines. A third camp takes a middle path. They concede the entire universe may never be directly observed, but argue its influence could still leave indirect traces. Just as detectives reconstruct a crime from scattered clues, cosmologists might piece together the mirror realm's existence through anomalies in gravitational waves, neutrino behavior, or the cosmic microwave background. These wouldn't be smoking guns, but a pattern of inconsistencies that point toward a deeper symmetry. It's the scientific equivalent of hearing a whisper in a crowded room, faint but unmistakable once you know what to listen for. The debate reveals a deeper tension in modern physics. How far can theory drift from experiment before it loses its way? Some fear the anti-universe crosses that line, while others see it as the next frontier. But perhaps the truth lies in recognizing that science has always balanced on the edge of the knowable, with today's heresy becoming tomorrow's textbook. Whether the anti-universe survives scrutiny or not, the questions it raises about time, symmetry, and the limits of observation are pushing cosmology forward in ways no one could have predicted. Supercomputers are giving us the closest thing we've ever had to a window into the anti-universe, not through telescopes, but through lines of code that rewrite the laws of physics. Teams at labs like CERN and the Perimeter Institute have built digital universes inside silicon brains, where gravity repels, time flows backward, and stars run on antimatter. The results are breathtakingly strange. Galaxies in these simulations don't spiral outward, they collapse inward, pulled by a repulsive force that turns cosmic expansion into a slow-motion implosion. Watch one of these digital anti-galaxies long enough, and you'll witness the opposite of a big bang, a big crunch, where all matter is drawn together into a single, searing point, as if the universe is rewinding itself to birth. These simulations start by flipping fundamental constants. Take gravity. In our universe, it's a positive value that pulls masses together. But in the anti-universe model, programmers input a negative gravitational constant, turning attraction into repulsion. The effects ripple through every calculation. Planets orbit stars by being pushed away at precise angles, like marbles rolling around the rim of an inverted bowl. Black holes, they become white fountains, spewing matter outward in violent jets. Even the cosmic microwave background, the afterglow of creation, shows inverted temperature patterns with cold spots where our universe has hot ones, as if the simulation is staring at a photographic negative of reality. One of the most startling discoveries from these digital experiments is how stars behave. In our universe, fusion ignites when hydrogen atoms crush together under gravity's pull. But in the anti-universe model, fusion happens when particles are pushed apart by repulsive forces, as if the very act of avoidance sparks creation. These anti-stars burn with a cooler, stranger light, their cores fusing antimatter into heavier elements in reverse order. Iron doesn't form in supernova, here it unravels into helium, as if existence itself is unspooling. The simulations also challenge our understanding of entropy. While our universe marches toward disorder, these digital anti-cosmos tidy themselves up over time. Gas clouds don't scatter, they coalesce into perfect spheres. Broken objects reassemble spontaneously, like shattered glass shards leaping back onto a table to form a pristine cup. It's a mesmerizing dance of self-organization, where chaos isn't the end state but the starting point. Researchers have even watched simulated anti-life forms, if you can call them that, emerge in these worlds, their structures growing more complex as entropy decreases, evolving backward toward simplicity rather than forward toward diversity. But here's the rub: these simulations aren't just academic exercises. They're stress testing the limits of our physics. When programmers tweak variables to mimic the anti-universe's inverted laws, they often hit mathematical roadblocks, equations that blow up or spit out impossibilities. Some theorists argue these breakdowns reveal flaws in the anti-universe idea itself. Others think they're clues hinting at deeper symmetries we haven't yet uncovered. It's like trying to translate a poem into a language that doesn't have words for half the concepts. The stumbles might mean the poem's untranslatable, or that the language needs to expand. What's clear is that these digital explorations are reshaping how we think about reality's boundaries. Whether the anti-universe exists or not, simulating it forces us to confront how fragile our intuitions are, how easily the cosmos could have chosen a different set of rules. And if one day these simulations start spitting out patterns that match anomalies in our telescopes like those CMB cold spots or backward-moving neutrinos, we might just find that the universe has been whispering its secrets to us all along in the language of inverted code. If time flows backward in the anti-universe, why doesn't our present feel like a memory of tomorrow? The answer lies in one of quantum physics' most mind-bending phenomena, decoherence. In our universe, the arrow of time emerges from the irreversible spread of quantum probabilities into definitive outcomes. A flipped cosmos wouldn't just reverse this process, it would rewrite how causality itself is perceived, like watching a movie where the plot only makes sense when run in reverse. Picture a quantum event, a particle existing in multiple states simultaneously until measured. Here, observation collapses those possibilities into one reality, weaving the fabric of now. But in the anti-universe, the process runs backward. Definite states unravel into probabilities as time progresses. For an observer there, a shattered glass would unbreak, not because time reverses in their experience, but because their version of decoherence reconstructs the past from future fragments. Their memories wouldn't recall tomorrow because memory itself is a product of entropy's direction, a record of increasing disorder. In a realm where entropy decreases, their past would feel like our future, a fog of possibilities slowly sharpening into certainty as events move toward what we'd call the beginning. This leads to the paradox of observer-dependent reality. Just as astronauts in orbit experience time slightly slower than those on Earth, an anti-universe being would perceive causality differently based on their local arrow of time. To them, our universe's events might appear predetermined, playing out like a film they've already seen. But here's the twist: neither perspective is correct. Reality fractures into valid but incompatible versions, each shaped by their own thermodynamic context. The future feels unknowable to us not because it doesn't exist, but because our consciousness is wired to surf the wave of entropy in one direction. Quantum mechanics offers a startling resolution. In the many worlds interpretation, every possible outcome branches into parallel timelines. The anti-universe could be one such branch, a reality where the quantum dice landed on inverted numbers. Decoherence there wouldn't just erase quantum superpositions, it would assemble them like a sculptor working backward from fragments to a whole statue. This duality suggests time's arrow isn't universal but perspectival, a cosmic illusion forged by the way entropy molds observation. The implications ripple beyond physics. If our experience of time is a byproduct of decoherence, then the anti-universe's inhabitants might not remember the future at all. Their consciousness could process events in reverse order while subjectively feeling like time flows forward, much like a rewinding tape still plays coherently to someone watching it backward. The real mystery isn't why we don't recall tomorrow. It's whether recall itself means something fundamentally different across the mirror. This paradox dissolves when we accept that memory and prediction are two sides of the same coin, stamped by entropy's direction. Our brains are entropy engines storing the past because disorder increases. Theirs might work oppositely, predicting the future because order does. Neither is more real, just reflections in a cosmic hall of mirrors, each convinced their version of time is the right one. The anti-universe doesn't break causality, it redefines it, proving that the arrow of time isn't an absolute law but a local habit, a quirk of perspective in a far stranger multiverse. Antimatter galaxies should be blindingly obvious if they exist. When matter and antimatter meet, they annihilate in bursts of energy visible across the cosmos. So why haven't we spotted even one? The Fermi Large Area Telescope has spent over a decade scanning the sky for these telltale explosions, hunting for the gamma-ray signatures that would betray entire galaxies made of antiprotons, positrons, and antihelium. Its observations paint a puzzling picture. Space is far too quiet. If antimatter galaxies were out there, the borders where they brushed against ordinary matter should light up like neon signs. Instead, Fermi's data shows only the faintest whispers of annihilation, nowhere near the cosmic fireworks expected from colliding stellar systems. This silence is more than just a missing observation, it's a paradox. The Big Bang should have created equal parts matter and antimatter, yet we're surrounded by a universe overwhelmingly made of matter. Some theorists hoped antimatter might have clumped into hidden structures, vast islands of anti-stars lurking in voids between superclusters. But Fermi's precision mapping ruled out even this elegant escape. The telescope can detect annihilation radiation from individual antimatter clouds as small as a grain of sand in a football field. That it's found nothing suggests antimatter galaxies either don't exist or are vanishingly rare. The implications reach beyond astronomy into fundamental physics. If antimatter didn't form large-scale structures, what prevented it? One possibility is that antimatter behaves differently under gravity, a notion that would upend Einstein's equivalence principle. Alternatively, cosmic inflation might have stretched regions of antimatter so thin they became undetectable. The most tantalizing explanation: antimatter didn't vanish, it's hiding in the anti-universe. If our cosmos has a mirror twin where antimatter dominates, Fermi wouldn't see annihilation radiation because the two realms are forever separated by the Big Bang's firewall. Yet the search isn't over. New telescopes like the upcoming Amigo mission will scan for higher energy gamma rays, hunting for subtler signals. Some scientists speculate that antimatter galaxies could disguise themselves. Perhaps their anti-stars produce light indistinguishable from ordinary stars, making annihilation their only giveaway. Others propose that antimatter might cluster in ways we haven't considered, like fractal distributions or dark matter-bound pockets. The deeper mystery isn't just where the antimatter went, but why the universe cares so much about the difference. Matter and antimatter are nearly identical, differing only in the tiniest asymmetries. That such minor quirks could determine the fate of galaxies and the viability of life hints at laws of physics we've yet to uncover. Until we solve it, the absence of antimatter galaxies remains one of cosmology's most profound puzzles, a cosmic missing persons case with no obvious culprit. The fate of our universe and its mirrored twin hinges on a cosmic tug of war between two opposing forces, entropy and symmetry. On one hand, the relentless expansion driven by dark energy seems to push the two realms further apart, as if the fabric of spacetime itself is determined to keep them separated. Galaxies race away from each other at accelerating speeds, stretching the boundary between realities like an ever-thinning rubber sheet. If this continues, the anti-universe could fade into an unreachable phantom, its gravitational whispers growing fainter until even quantum links between particles snap, leaving both realms forever isolated. But there's another possibility, one that turns the Big Bang from a beginning into a midpoint. If dark energy weakens over time, or if gravity's repulsive grip in the anti-universe falters, the two could begin collapsing back toward one another. Picture it like a cosmic pendulum. The initial explosion sent our universe flying outward while its twin recoiled in the opposite direction. But what if the swing reaches its peak and reverses? Matter and antimatter, entropy and negentropy, forward and backward time, all would rush toward a cataclysmic reunion. This wouldn't just be another Big Bang, it'd be a big bounce, a moment where physics folds in on itself like a Möbius strip, recycling existence in an infinite loop. Entropy plays the referee in this dance. In our universe, increasing disorder drives time's arrow forward, but in the anti-universe, entropy runs backward, creating a bizarre paradox. As our cosmos degrades toward heat death, its twin grows ever more ordered, like two climbers on opposite sides of a mountain, one descending into chaos, the other ascending into structure. This imbalance could destabilize the boundary between them, forcing a collision not despite their differences but because of them. Like two puzzle pieces cut from opposing molds, their very asymmetry might lock them back together. Yet the math reveals a twist. If the universes collide, their mirrored entropies wouldn't cancel out, they'd amplify. The meeting point could unleash a phase transition far stranger than a bounce, a moment where causality shatters entirely. Time might fracture into loops, with fragments of each universe embedded in the other like shards of glass in a kaleidoscope. Some models even suggest the collision would birth not two universes, but infinite ones, a fractal cascade of realities, each with their own inverted physics. The haunting beauty of this idea is that we may already carry evidence of past collisions, those enigmatic cold spots in the cosmic microwave background. They could be scars from previous cosmic embraces, bruises left by a twin universe pressing against ours in an earlier cycle. If so, the ultimate fate of our cosmos might not be heat, death, or eternal drift, but an echo, a rhythm of collision and separation playing out on scales so vast they defy comprehension. Whether the next act brings union or solitude, one thing is certain: the universe has never been alone, and its story is far from over. The moment we confirm the anti-universe exists, humanity would face an ethical dilemma unlike any other. Do we reach out or do we stay silent? At first glance, communication seems inevitable. The urge to connect is wired into our DNA, from ancient campfires to radio telescopes scanning the cosmos. But this isn't just saying hello to extraterrestrials. It's poking a mirror where the fundamental rules of reality are inverted. Imagine sending a signal across the divide, only to trigger a chain reaction that unravels space-time itself. Theoretical physics suggests a nightmare scenario: vacuum decay. If our universe exists in a metastable state, a precarious valley in the landscape of quantum fields, contact could nudge it into a lower energy state. The result, a bubble of true vacuum expanding at light speed, rewriting the laws of physics as it goes, erasing stars, planets, and life itself in an unstoppable wave of annihilation. Yet the risks might be even stranger in reverse. If the anti-universe operates under opposite thermodynamic laws, our attempts to communicate could appear as destructive interference, there a burst of entropy flooding their ordered reality. Their time-reversed perspective might interpret our signals as attacks, like watching a video of an explosion where the flames rush inward to assemble a bomb. Even harmless math, like prime numbers pulsed via radio waves, could manifest unpredictably in a realm where cause and effect are inverted. The very act of observation here might collapse quantum states there in ways we can't foresee, like shouting into a cave and hearing the echo before your voice leaves your lips. But isolation carries its own perils. If civilizations in the anti-universe exist, they could possess knowledge that solves existential threats, from climate collapse to asteroid impact. Their inverted physics might reveal shortcuts through quantum entanglement, enabling instantaneous travel or unlimited energy. There's also the philosophical reward, confirming we're not alone in the multiverse, just asymmetrically paired. Picture humanity's greatest art and science sent across the mirror, only to return as fragments of alien masterpieces we can't yet comprehend, a cosmic call and response spanning dimensions. The debate splits along fault lines deeper than science. Some argue the precautionary principle demands silence. We've seen how first contacts on Earth ravaged indigenous cultures, and this could be exponentially worse. Others counter that stagnation is its own existential risk, that a species too fearful to reach beyond its horizon seals its doom anyway. Perhaps the answer lies in passive observation, studying their universe's gravitational echoes or quantum noise without transmitting. Or maybe we're already in contact without realizing it, with neutrinos and dark matter particles acting as natural messengers in a dialogue we're only beginning to decode. One thing is certain: the decision can't be ours alone. Any protocol for anti-universe communication would require global consensus, a treaty spanning nations and generations. Because once the signal is sent, there's no undo button, only the uncertain ripple of consequences flowing outward through the mirror and back If the entire universe stretches our understanding of reality to its breaking point, then nested universes and fractal cosmologies shatter it entirely. Imagine a cosmos where every black hole in our universe births an entirely new reality inside its event horizon, not just a mirrored twin, but infinite layers of existence stacked like Russian dolls. This isn't fringe speculation, it's a serious hypothesis from physicists like Lee Smolin, who propose that universes evolve and reproduce through black holes, each with subtly tweaked physical constants. Stars collapsing here could be big bangs elsewhere, their deaths giving rise to entirely new space-time fabrics where gravity is stronger, light slower, or entropy reversed. The implications are dizzying. Our universe might just be one branch on an endless cosmic family tree, with roots stretching back to some primordial ancestor reality. Now take that idea and fractalize it. Instead of linear nesting, picture a cosmos where every scale, from quarks to galaxy clusters, contains self-similar patterns of reality. At the quantum level, tiny universes flicker in and out of existence, their brief lives mirroring the expansion and contraction of our own cosmos. Zoom out, and our entire universe might be a single particle in some unfathomably vast superstructure, like a drop of water in an ocean we can't perceive. This isn't just poetic analogy. The math of holographic duality suggests our three-dimensional reality could be a projection of information encoded on a two-dimensional surface at the universe's edge, like a cosmic version of a hologram where depth emerges from flatness. Higher dimensions add another layer of strangeness. String theory proposes at least 10 dimensions curled up at scales too small to detect, like the folded grooves of a vinyl record surface. But what if some of those dimensions aren't just hidden, they're inverted? A 5-dimensional mirror could reflect our universe in ways that make the entire universe seem tame, with gravity leaking between dimensions or time branching into fractal pathways. Imagine beings who perceive time as we perceive space, able to walk forward and backward through moments like strolling down a street. Their past might be our left, their future our right, rendering causality as malleable as putty. The wildest twist, these theories aren't mutually exclusive. Our entire universe could be one reflection in a higher dimensional hall of mirrors, its black holes birthing fractal offspring, all while existing as a holographic projection on some distant boundary we'll never see. Reality might not just have layers, it could be an onion with infinite skins, each hiding truths more bizarre than the last. The only certainty is that the cosmos has yet to run out of ways to surprise us. The entire universe isn't just a scientific hypothesis, it's a breathtaking cosmic riddle, wrapped in symmetry, whispering questions that redefine reality itself. Whether it exists or not, the sheer elegance of the idea forces us to confront how little we truly understand about existence. From mirrored time and inverted gravity to black holes that might bridge realities, this theory stretches our imagination to its limits, revealing just how strange the cosmos could be. It's not just about antimatter or backward physics, it's about the possibility that everything we know is half of a grander, stranger whole. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." The entire universe embodies that spirit, an unanswered question hanging at the edge of science, daring us to look deeper. Maybe it's out there, balancing our universe in perfect opposition, or maybe it's just a mathematical mirage, a beautiful trick of the equations. But here's the real magic: the search itself changes us. Every bold idea, every wild possibility, pushes the boundaries of what we think is possible, turning science into the greatest adventure of all. So now it's your turn. Do you think the entire universe is real, a hidden twin waiting to be discovered? Or is it just a sci-fi dream, a mind-bending what if that will never leave the realm of theory? Drop your vote in the comments and let's keep the conversation going, because whether it's fact or fiction, one thing's for sure: the universe or universes will never stop surprising us. The next great discovery might be just around the corner, or maybe just beyond the mirror.